In terms of manufacturing and marketing electric vehicles, creating electric batteries, and pretty much everything else related to electric mobility, China leads the globe.
When you drive a Chinese vehicle today, it's far different than 10 years ago. They are better built, and the quality overall is much more competitive with what you would see from a US automaker or from a European brand.
And now China has been included once more since it has developed a new electric motor called a plasma motor, which is expected to revolutionize mobility and transportation. What is a plasma electric motor? Exactly. How does it operate too? Come along as we examine the newest plasma electric motor from China. In the current world, air travel is one of the most practical and well-liked forms of transportation. It links people, economies, and cultures worldwide. It does, however, come at a significant environmental cost. The International Civil Aviation Organization estimates that in 2018, the world's aviation industry contributed around 2.4% of all CO2 emissions. In addition, additional pollutants released by aircraft engines include water vapor, particulate matter, and nitrogen oxides, all of which have an impact on the climate and air quality. Recent advancements in this topic include the creation of a working prototype of a plasma jet device within the atmosphere by Wuhan University scientists in China. The apparatus creates plasma using air and microwaves, which is capable of lifting a 1 kilogram steel ball over a quartz tube. According to the researchers, this is comparable to the thrust of a commercial jet engine, and by using an array of plasma thrusters, the device may be scaled up to power bigger aircraft. This innovation may usher in a new age of environmentally friendly aviation that is more efficient and sustainable than before. However, before plasma engines become a reality, there are still a lot of obstacles and unknowns to be resolved. For example, how to assure their safety and dependability, how to integrate them with current aircraft designs, and how to provide enough energy to power them. We must first define a plasma propulsion engine before moving on. Most people consider plasma-based thrusters to be a viable option for spaceship propulsion. Unlike ion thrusters, which produce thrust by drawing ions from a plasma source and then accelerating those ions with the use of specific grids or anodes. These engines operate in a different way. In contrast to ion thrusters, most plasma engines can accelerate the charged particles in the plasma source without the need of high-voltage grids or anodous cathodes. Rather, they accelerate the ions using the electric arc that forms between two electrodes. This method usually results in a reduced velocity of the exhaust particles due to the restricted voltage used for acceleration. But these engines don't require particularly high thrust, since there isn't much air resistance in space. They can ultimately reach very high speeds if they can accelerate continuously for months or even years. Comparing these engines to other forms of electrical propulsion reveals a number of advantages. For example, the likelihood of high-voltage grids or anodes deteriorating as a result of ion erosion is decreased. The quasi-neutral plasma exhaust, which has about equal amounts of positive ions and electrons, is another benefit. The exhaust plume is essentially eliminated by this equilibrium, which permits the ions and electrons in the exhaust to simply recombine. That means you don't need an electron gun. These engines usually use a variety of techniques, such as the use of microwave or radio frequency radiation through an external antenna to produce the plasma. These engines' architecture enables them to run on a variety of propellants, such as carbon dioxide, argon, and even human urine. What makes this new Chinese plasma engine so unique then? Chinese engineers unveiled a working microwave thruster prototype last year. According to these experts, the engine's efficiency and thrust in the Earth's atmosphere might be on par with those of conventional jet engines, since they usually need noble gases like xenon, Plasma engines haven't shown to be viable in Earth's atmosphere. This is because air friction causes the ions they produce to lose propulsion. Furthermore, the thrust produced by current plasma engines is rather moderate, making them enough for space but inadequate for Earth. Researchers from Wuhan University's Institute of Technical Sciences have created a new design that adopts a different strategy. It functions by utilizing air and electricity as opposed to gases like xenon. Tests have shown that this engine is capable of producing a significant amount of thrust, which may lead to new uses for sophisticated aircraft in the future. This novel plasma engine operates in a manner similar to that of a combustion engine. To generate propulsion, a source gas is turned into plasma by quickly heating it and then expanding it. Ionized air is used in this novel engine to produce a low-temperature plasma. To guide this plasma into a tube, an air compressor is used. The air is subjected to microwaves as it passes through the tube, which violently shake the ions and cause them to collide with non-ionized atoms. The plasma's temperature and pressure are greatly increased during this collision event, which produces a tremendous push further down the tube. A rectangular metal tube known as a waveguide that has been flattened is partially responsible for this amazing accomplishment. This guide directs the microwaves produced by a 1 kFA 245 GZ magnetron that was custom developed. As the guide approaches the plasma, it narrows to half its initial size before widening once again. Through this manipulation, the electric field's intensity is increased and the amount of heat and pressure that is delivered to the plasma is maximized. In addition, a quartz tube is inserted into a hole at the waveguide's narrowest point. Air is forced through the quartz tube, out the other end, and through a little portion of the waveguide. The whole procedure is made easier by this configuration. What is this engine's power? The scientists noticed a fascinating phenomena. The flame jet created within the tube would actually grow longer when the airflow in the compressor was eventually regulated. This was done by increasing the microwave power. They made an effort to gauge the engine's thrust output as a result of this observation. That being said, there was a big obstacle to overcome. When a standard barometer used for thrust measurement was subjected to temperatures as high as 1000 degrees, the engine created a plasma jet that would have destroyed it. The team came up with an unusual way to deal with this issue. They came up with a way to keep a hollow steel ball balanced above the tube. Small steel beads were used to fill this ball, enabling the weight to be changed as required. The ball would stay suspended at a certain height above the tube. When the thrust reached a particular level and offset the force of gravity, pushing the ball downward on the exhaust end of the tube, they were able to measure the engine's thrust indirectly thanks to this ingenious technique. Through the use of this special measuring technique, the study team calculated the thrust generated by the plasma jet. They achieved this by taking a measurement of the steel ball's suspension length above the tube and deducting the compressor's thrust. They were able to do testing with different power levels and airflow rates thanks to this creative method. They were surprised to see a direct correlation between airflow and microwave power, as well as the propulsive force. Moreover, the technique demonstrated remarkable efficacy. With merely 400 watts of electricity and an airflow velocity of 1.45 cubic meters per hour, it could produce 2.5 pounds of thrust or 11 newtons of propulsive force. This corresponds to a 6.29 pounds of thrust conversion rate or 28 newtons per kilowatt of electricity. To put this into context, a Tesla Model S battery with an output of 310 kilowatts might be able to produce around 1911 pounds or 8.5 kilonewtons of thrust force, assuming this linear connection holds true. Comparatively, the now cancelled Airbus EFAN two-seater electric aircraft used 230 kW electric ducted fans to provide around 1.5 kilonewtons of static engine thrust. This indicates that the researchers' prototype which has a thrust-to-power ratio of around 5.62 pounds, or 25 newtons per kilowatt, provides better efficiency. Although the new plasma-based thruster technology is fascinating, it may have trouble finding a place in the growing market for electric vertical takeoff and landing, or eVTOL, aircraft. Although the engine creates a stream of plasma at a searing 1,000 degrees Celsius, this might raise serious safety and environmental issues, even if it is quieter than ducted fans or regular propellers. Furthermore, owing to certain restrictions, the technology may not fit into the eVTOL environment readily. These engines operate at far lower airflow rates than full-sized engines, and the thrust scaling needed for them requires a huge increase in power, which comes with its own set of difficulties. One may be disappointed if one tries to draw linear patterns across such large ranges. The study team's data has numerous odd gaps that critics have pointed out. Notably, the data does not include the prototype's maximum microwave power levels at its maximum air velocity. The reasons for these deletions are yet unknown. This technical advance is still fascinating, however, given the trend away from fossil fuel-based power sources. The novel plasma-based thruster design has the potential to represent a substantial leap in aircraft propulsion if it proves to be both scalable and efficient. Although there are obstacles to overcome and information gaps to close, this breakthrough creates intriguing new possibilities for aviation propulsion systems in the future. What are your thoughts on this? Tell us in the space provided for comments.